Hi, in this video, we want to talk about logistic regression, specifically for the purpose of supervised learning. All right, logistic regression is by far the most common way to classify doing supervised learning, a predictive model to predict the value of two possibilities. And so this might be success, failure, on, off, broken, not broken, sick, well, male, female, something like that. And so what we want to do, we want to be able to use logistic regression to make predictions about the futures. All right, so something that's very important is that we have a binary response variable. So our target variable has two possible levels. Now, what we're going to do most of the time, most typically, we're going to code those levels into zeros and ones, and then we'll proceed in our analysis. So when I get my results, I have to remember how did I code it in the first place. R, if I'm using base R, will actually be able to handle two different levels uh, without having to be coded, which is nice. It makes it easier to interpret. But frequently, when I'm doing my averages and my computation, so if I take a mean, zeros and ones are very nice because it gives me the fraction of successes. Um, so regular old regression, linear regression models focus on continuous outcome variables, while logistic regression predicts the probability of an event occurring. So it models the probability of success or probability of one. All right, so here's some examples that we could have. So maybe we want to build a model that, like we work for IT and we have email coming in and we want to mark it as spam or not spam using logistic regression. Maybe in a medical setting, we want to create a model that predicts the likelihood that a tumor is malignant or benign. And there's also maybe in an academic setting, we want to predict the likelihood that a student will fail or pass a class or a test. Um, all right, so first thing I'm going to do is set my workspace as always. Here I am making sure that we're rounding off digits because I don't want to see more than I'm going to use in interpretation. Increasing the side pin value makes R try to avoid scientific notation. And I'm going to suppress warnings when I can because most of the time, like with the code that I'm showing you, warning, I already know what's up. I don't have to be, I don't need like messages, flashing in front of my face. I'm removing any artifacts from my workspace to make sure I don't have any conflicts. And I'm going to be using piping. So I'm going to invoke the McGritter package. All right. So now a question you could ask is like, why do I use logistic regression? Why can't I use linear regression? All right. So linear regression, makes a prediction on values between negative infinity and positive infinity. Okay. And so it goes the full possible range. Now, if I only have two levels, like how do I coherently connect back and forth between the entire real line and the zeros and ones or the two different levels? So the predicted values are outside of really what's an interpretable range. So we'll get nonsense values. Also, we can have problems with heteroscedasticity, and we can have nonlinearity of the predicted probabilities. Also, linear regression makes several assumptions that we don't actually make an assumption on. So here, linearity, right out the gate, if I'm trying to use linear regression, the assumption just doesn't even hold. The linear relationship makes the assumption that I have a numeric response variable, and I know right out of the gate that that's not the case. So a violation, the first violation is violated if I'm going to do this. Now, we in all of these, we need independence and homoscedasticity for what we're working on. But normality, so these two are necessary either way for logistic regression or linear regression. But normality of residuals is not actually assumed. Logistic regression is more flexible on this one. And so if I let's say I tried to shoehorn a linear regression model to perform for logistic regression, more than likely we're going to end up having biased and incorrect estimates. And so I really don't want to even try this. All right, so now let's talk about some data preparation for logistic regression. So first thing I'm going to do, I'm going to load my data. If you recall from previous video, I already went through and prepared the mushrooms data set. So here, 1 is edible, 0 is inedible or poisonous. And in this data set, this is a Kaggle competition data set. And so I'm going to take the data and I'm going to create a train test column for splitting so I can do my train test statistics. Now for my data prep, first thing I need to do, I need to make sure that my target variable is binary. Now, R will actually handle factors, 2-level factors, as a response variable. But what if I made a mistake and I coded it with 3 levels? It's not going to work out. And frequently we just make it easier on the machine. It's standard practice to have 0s and 1s, but I have to remember which level is 1, which one's 0. So for us, 1 is edible, 0 is poisonous. Now we're going to need to handle missing data. So in logistic regression or regular regression, missing values cannot be in the training data. So R by default will kick out any rows of data that have 1 or more missing values. All right, well, if I'm losing that, really I should be taking care of that beforehand. Either I should manually remove them so I understand what's going on, I have a better feel for what's happening, or I should impute the missing values. So omission is our first strategy for missing data. That is where we remove any record, any row with 1 or more missing values. And something that's kind of interesting, if I had 1,000 columns of data and 1 observation was missing, then the entire row would be omitted. Well, that's kind of extreme. And so frequently, instead, we're going to want to fill in the blanks with reasonable values. That's called imputation. And there's a bunch of different ways to do imputation. First one is univariate imputation, where we fill in a reasonable value. Frequently, we use the mean of the column or median of the column. I prefer the median, by the way. Or we can use k nearest neighbors to fill in, or we could use like a regression, or basically use any other type of model we could use. My personal preference is to use the misranger package uh, if that's appropriate for my project. Now, outliers are going to be a problem just like they are with regular old linear regression. Now, logistic regression is more robust to outliers and violations to non-normality, but this is still an issue. I want the best data possible. So one thing I'll want to do, I want to deal with outliers. Maybe I want to cap the values, like mute them down, or possibly omit them, or maybe just remove an outlier altogether. And for the non-normality aspect, I might want to consider like a Box-Cox or Yo-Johnson transformation. Now, feature scaling, here's where we don't have to do both of these, but we have 2 options. We can subtract by a constant, typically the sample mean, and divide by a constant, typically divide by the sample standard deviation. Now, so that would give us the column mean of 0 and a column standard deviation of 1. Now, why would we like to do this? This will result in having coefficients that are easier to interpret. And so it's easier to figure out what's important in terms of variable importance after I do this. Now, it's going to work out that in logistic regression and in multiple linear regression, feature scaling will not improve model performance. It will improve model performance in things like k-nearest neighbors and support vector machines, but not with logistic regression. So this is optional. I like to do it when I'm doing my first run at model exploration before I decide on the model structure, but you could skip over it. It wouldn't be a problem. Now, something that we also need to worry about is that linear regression and logistic regression and generalized linear models cannot handle categorical data as straight categories. We need to deal with them some way. So either we need to do dummy variables, or we need to do categorical smoothing. That's where we replace the value of the category with the conditional average of the target variable based off of what category we have. And that works out very well. In general, the most common data prep that we do for categorical data is going to be binning. That's very important. All right, so now how is the model fit for logistic regression? Well, this is different than linear regression. In linear regression, we're attempting to find the coefficients that minimize the sum of squared error. Here, we're going a different route. So we're going to maximize the likelihood estimation. Okay, so what is maximum likelihood estimation? Well, what we're going to do, we're going to take a probability distribution, and that's how I'm going to get my likelihood. So I'm going to take my data, I'm going to apply a probability distribution, and then that's going to give me a likelihood. Well, what I want to do, given the distribution situation I have, I want to find the parameters that maximize the likelihood. So it's the maximum likelihood estimation. All right, so something to consider is the difference between likelihood and probability. All right, so probability, how we want to think about that is that that's a chance of something occurring before it has happened. That's the probability of an event. Now, likelihood is measured on the same scale, but slightly different. Think about flipping a coin. Before I flip the coin, assuming it's fair, what's the probability of getting ahead before I flip? Well, it's 50-50, so I've got, 50% chance. Now, let's say I flip that coin, and then before I see it, I cover it up. Now, what's the probability of head? Well, it's 0 or 1. Either it's a heads or it's a tails. It's 0 or 1. There is no randomness. There is no probability aspect to it. Now, what's the likelihood of a heads? Well, it's going to be 0.5, 50%. So likelihood, deals with probabilities like before or after the event has occurred, but probability is for random events that have yet to occur. All right, so a maximum likelihood estimate. What we're going to do, how this is actually scored and worked out, is that I'm going to take the binomial distribution and I'm going to apply that for every single row of data. All right, so here, say X is all the different values for the predictor variable. And so our mathematical model is that once I see all the predictor variable values, there is a probability that it's going to be a 1 or a 0, okay? So here's so once I see all of the values, there's a probability of it being 1 or 0, and this is a probability of 1, and this is a probability of 0. Now, I'm going to invoke the Bernoulli distribution. So for each individual data point, either it's a 1 or it's a 0. And so if this y is either a 1 or a 0. Okay? And so now we can see that corresponds to the ith observation, and this is the likelihood of what we've got for that individual observation. Now, assuming that we have independence between all our observations and we have identical distributions, then it's going to work out that the likelihood overall of the entire data set is what I would get from multiplying these for every single observation, multiplying them all together. And that's what this symbol says. It says multiply all of them together. So for observation 1, score this. Observation 2, score this. Observation 3, score this. And keep on going all the way up to observation n. Then what I'm going to do, I'm going to multiply all those together. Right, and that's going to give me my likelihood. All right, so in logistic regression, I know what the x's are, I know what the y's are, but I don't know this p. So what we're going to do is that we're going to work to find the function for p that gives us the largest likelihood possible. And so the beta represents all the coefficients that are in our logistic regression model. All right, so here, that P that I just talked about previously, this P of X is equal to this. So after I know the value of X, this fraction is going to give me the probability of 1 given I know all the values of my predictor variables. And so what's going to happen for large positive values here, so if this linear combination is large and positive, then this value is going to be, that E is going to be large and positive. Or I'm going to have a large positive value divided by 1 plus a large positive value. Okay, so think about your calculus for a moment. Let's say I have a million divided by a million plus 1. The difference between a million and a million plus 1 is negligible. This will be super, super close to 1 if the exponent is very, very large. Now think about the opposite direction. What if this value here, the exponent, is large and negative? Well, if it's large and negative, then this E is close to 0. Okay. And this E is close to 0. All right, so then I get something that's close to 0 divided by something that's just a little bit bigger than 1. Well, 0 divided by anything is 0, right? So the whole thing is close to 0. So if I have an extremely negative linear combination, I'm going to get probability close to 0. Now, what if the linear combination is equal to 0 itself? Well, then e to the power of 0 is 1. So the top is 1. On the bottom, this is 1. 1 plus 1 is 2. So this is equals to a half. So when the linear combination is equal to 0, my probability is 1/2. Now, to fit the model, we're going to use the generalized linear model, GLM function in base R. And we need to specify our formula. We specify our data. And, oh, I neglected to restrict it to the training set. And then we need to specify the family. For logistic regression, we need to specify that it's the binomial family. Now, I do not need to specify the link. The default is logit. There are multiple link functions that we can use. Logit is by far the most common to use. It has a lot of nice theoretical properties, and I feel like it's the best choice overall. The link function is the inverse of an activation function in neural networks, by the way. All right, so now we have our coefficients for maximum likelihood estimate. If I see a positive value, that indicates that increasing that predictor variable will increase the likelihood of seeing a 1 from my model. And we can get residual deviance, and we can get AIC to help us analyze what's going on. The coefficient function will extract the coefficients, and we can run hypothesis testing on all of our coefficients. And you notice that odor could be removed from this more than likely. Before the video, I did backwards elimination, and the backwards elimination model had a lot more predictor variables, so I removed them to just keep things simpler. It looks, some criteria of the model that I built look overfit, so I went ahead and just kept on simplifying the model down. And we get our number of iterations. A good rule of thumb across the board for any model structure, if it takes a lot of iterations to converge, when it's not that complicated of a model, like just relative to complexity, it takes a lot of iterations to converge for a model. That's a good sign that you have a bad model structure, that your data and your model don't match up together very well. And for ANOVA, we don't actually get an ANOVA table. Remember, we're not doing our whole minimized sum of squares error. We're doing maximum likelihood. So instead, we have our deviance to interpret. And so now we can go ahead and plot. So just like with generalized linear models, just like with linear regression, our plot function gives us 6 possible plots. And something I like to do, I like to color the plots by the target variable to help me, identify what's going on. And so something that's in these plots is that every single time R is going to label the most three extreme points. And these are, think of these as candidates for outliers. And these are, on top of each other. And this corresponds to the row name in the data set. So here it's just the row number. We have Cook's distance. And we see that, the red is where we're having more Cook's distance. The edible have, pretty consistently small Cook's distance, while the red does not. That's kind of interesting. I might want to dig into that deeper. And we get our residuals versus leverage. Cook's distance versus leverage. All right, so now let's think about that equation that we did a moment ago, where I had that e to an exponent over 1 plus e to the exponent. Well, that's an invertible function. What am I going to get if I take the inverse? Well, the inverse is going to be the log of the probability of success divided by the probability of failure. Okay, so here we're going to call this the odds. So I'm going to the probability of success divided by the probability of failure is our odds, and then I'm going to take the logarithm of it. And so that is the log odds. All right, so using the inverse function aspect, we can see that the log odds is equal to that linear combination. And so when we get a result, R under the hood is actually working on this function, this equation, not the one that we presented a moment ago. What we do manually, we convert this over to that E fraction for the purpose of getting actual probabilities and likelihoods. And so, estimating using maximum likelihood is just like what I said before with using the whole Bernoulli situation of multiplying, multiple together. And then, I'm trying to maximize. I want to find the coefficients, values that maximize this over here on the right. Whatever values of the coefficients maximize the likelihood, that is going to be my estimated values. All right, so for continuous predictors, 1 unit increase in the predictor results in a change of beta in the log odds. So check this out. When I look at this presentation, if I was to increase x1 by 1, then what would happen is my log odds would increase by beta 1 by that amount. And so for a continuous random variable, or a continuous predictor, I should say, the coefficient indicates how much of a change, if I change my predictor variable by 1, how much of a change will I get in my log odds? Now for categorical predictors, the coefficient represents the difference between the baseline and the amount of increase if I was to change to that particular value of the category. All right, and so here, remember to be able to estimate, we're going to end up using the GLM function, and I want to put in binomial. Now here, I actually don't have to call this function. You notice I'm calling a function here. I don't have to. I can actually have a character string. If I put a character string of the family for the generalized linear model, it will run with default settings. For the purpose of this video, I put the function presentation so that way you could see where does the link function play its part. All right, so there are a whole bunch of different link functions, and we're going to talk about the more common ones. These are the ones that are in base R. There are other ones, but you're going to have to pull in other packages within R to get to them. I'm not going to talk about them. So the loglink, the logit link, is that log odds. And this is by far the most common one. This is probably the one that you want to use. Here, this is a very flexible link. So let's say that I need to build a model and I should have used a different link function than logit, but I chose logit. I made a mistake. it ends up that most of the time it's not a big deal. The loglink is very flexible and usually does a better job of handling misspecification of the link function than other link functions. And so if you don't know, go log it. It's the default setting, just run it. And so our interpretation of the loglink is that the coefficient is how much my log odds, so here's my log odds, would increase if I increase the corresponding predictor variable by 1. Now the probit link, this is connected to the normal distribution. And so you'll see that the formula here, I have the inverse of the normal distribution involved in this. This is the quantile function for standard normal. All right. And so a lot, in my experience, social scientists and economists like the probit link. I don't really, I've never had it be the best model for me. Well, actually, no, I take it back. I've had it once be the best model, but logit was really close behind it. And so I've never launched a model with probit because every time logit was was either the best or close to the best when I was working professionally. And so there, I can look at this equation and I can use the quantiles to connect standard deviations to increases in my my predictor variables like that. Now the cohesit link is where instead of using normally distributed, we're using the Cauchy distribution. And so you'll notice here I've got this should be inverse tangent. No, this is tangent. This is okay. We're invoking inverse tangent on this. I'm subtracting 1/2 from my probability, so that goes from negative 0.5 to 0.5, and then multiplying by pi. The inside here goes from negative pi over 2 to pi over 2, and so we're within the standard domain of the tangent function. And so the Cauchy distribution has very heavy tails. And so if I'm anticipating things to be like very extreme and very little in the middle, this is a better choice than probit. But the Cauchy distribution is kind of hard to work with at times because it doesn't have an expected value nor a population variance or any of the other moments. Now we also use the log link, where here we're just taking the log of the probability. So if you remember the logarithm function, at 1, it's equal to 0. And then for values greater than 0, less than 1, I'm going to have like an asymptote shooting down to negative infinity as the value gets closer and closer to 0. And so that stretches out that probability. That might be important for what I'm working on. And then C log log, this is a complementary log link. This is useful in survival analysis. And I've only used this in survival analysis, never used it in any other situations, but it's a tool in our tool belt. And so I've never used it for the purpose of logistic regression, but you can if that ends up being the best model possible. Remember that when we're talking about supervised learning, almost always our primary focus is to get the best prediction possible. To get the best prediction possible, I'll consider any of these link functions. All right, so I want to talk a little bit more about the logit link function. And so here, this is our log odds. And by taking the inverse of this function, I can see that the probability of success is equal to this. Notice I've got logarithms. And so when I put down log, I didn't say this. When I put down log in this video, that's natural log, not base 10. Statisticians, when we say log, almost always we mean natural log. And so if I take the inverse of this, I'm going to get this equation after I replace this g of p with the linear combination. And The loglink is very, very flexible. This curve here is going to be an S shape, absolutely guaranteed. And it's going to be symmetric about 0.5. This flex is so flexible that most of the time, this will be, if it's not the best, nearly the best link function to work with for most situations. And so if I misspecify the link function, it's usually not a problem if I went with logit because it will be close enough. Now the odds ratio, remember that my odds ratio is the probability of success divided by the probability of failure. And our log odds is equal to our linear combination. Notice now also something that's different from regular linear regression. You notice I don't have an epsilon term. I don't have an error term. When I'm handling anything in generalized linear models, including logistic regression, we are modeling the expected value. The expected value is a constant, and because of the randomness that's involved in such situations, I don't actually impose a random term on my equation. Now, if beta is equal to 0, that means that my predictor variable has no influence on what's going on. And so I won't have any change if I increase or decrease the corresponding predictor variable. Now, if e to the power of beta is greater than 1, then increasing my predictor variable will increase the likelihood of success. While if e to the beta is between 0 and 1, the probability of success will decrease if I increase the predictor variable's value. Now, to make predictions, we're going to want to use the predict function. Now, there's a catch with this. There's a pitfall. You got to watch out for this one. The default for GLM predict values is going to be the link function. Sorry, not link function, the link value. So here it's going to spit out that log odds instead. So here, the default of the predict function when I put in a generalized linear model is to get that log odds, not the probability that I actually want. And so if I want the actual probability, I have to put in response for the type. And now, boom, you'll notice I have a bunch of probabilities. Hey, now that's going to be easier for me to interpret as a human being. Now, I also have the option of putting type equals terms. And what this is going to do is that for each predictor variable, each row and each column, it's going to say how much what did each predictor variable contribute to that log odds. Now, for model validation, the most important one that we want to use, and believe it or not, like right before I left work, I was doing exactly what I'm about to talk about right here, right now. I built up a confusion matrix. And so remember that when I fit my model, I want to use my training data and I want to use my test data to see how things are going to respond in the future. And so I'm going to use the caret packages confusion matrix. That's very nice. It produces the results very nice for me and spits out a bunch of statistics so I don't have to go searching for them. Just one thing about this is that I have to have factors in being passed into my confusion matrix. And so here we can get the accuracy. So that's a darn accurate model. Confidence interval of the accuracy. I get the actual confusion matrix. So this is saying that prediction of poisonous was 100% accurate. But when I said edible, 53 times I was wrong. 53 times out of over 2,000. I mean, that's 2.5%, 3% error rate when it says it's edible. Would you take that risk for an edible poisonous mushroom? And we also get our p-values, kappa. We get McNemar's test, our sensitivity, specificity, and our, let's see, where's recall? Oh, it didn't give me recall. I thought it did. Now, variable importance here, this is going to be the absolute value of those t statistics that we looked at previously in the summary. And that's going to give us a measurement of how important our variable is. It's going to be the absolute value of the t-test statistic. Other models will have different ways of determining what variable importance is. Now, Wald's test, so we also can, so here's that, sorry, it's a z-score. I said t, that was incorrect. The absolute value of the z value is our measurement of variable importance. So here, by that measurement, we can see that population is the most important predictor variable, then gill color, then bruises, and after that would be odor. And usually we don't worry about the intercept in such situations. Now, we can also do bootstrapping to get a better idea of variable importance. We can get an entire distribution of any statistic I possibly want, including variable importance. And so that bootstrapping is really nice in that I can get an actual distribution of any statistic that I want to give me more insight to what's truly going on. Another thing that we can do to check to see if a variable is important is that if I remove it and I look at my model and my model's accuracy did not decrease, then it's not really an important variable. But if I take a variable out and accuracy of my model plummets, then I know it's an important predictor variable. Now we can get our variable importance real easily from the model using var importance, variable importance. This is a generic function for any model structure, not almost any model structure that caret can work with. And so here I'm just showing this really for future ones, but you can see that this is the absolute value of that z-test statistic list that we had previously. And one that is super important is our ROC curve at AUC. AUC is the area under the curve. Now that curve is here. So what's going to happen is that each dot along this line indicates that corresponds to a cutoff for the probability to say poisonous or edible. All right, so here we have a very low cutoff for saying that it's edible. And then a little bit higher, 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 until we say only if it says 1 will we call it edible. And so what's going to happen is that I have control over like the lopsidedness of this. And so I can set up so that maybe one mistake is worse than the other. Remember, we're talking about poisonous and edible. It's okay to call something poisonous when it's not, but it's not okay to call something edible when it's poisonous. So there's two types of mistakes going on. What I can do is I can set the criteria for what is edible really high to make sure I don't make a mistake and eat a poisonous mushroom out in the woods. And this curve, it gives me an idea of what's going on along that entire range of requirements from 0 to 1. Most of the time, by default, we put it at 0.5, but we don't have to. Now, the area under the curve is the area. If I look at this curve, I can see that if I go straight down, I've got a polygon, and there's an area to it. And so the best possible model will have an area of 1. The worst possible model will have an area of 0. Now, something that's kind of interesting is that if I was to just do random guessing, let's say I did a random number generator and I said, if the random number is greater than 0.75, I say edible. If it's less than 0.75, I say it's poisonous. And that would be about here. And so this would give me the rate at which I make each type of mistake. If I say, all right, if it's greater than 0.25, the random value, I'll say it's edible. If it's less than 0.25, I say it's poisonous. This is about where that would be. And I have a continuum along this line. And so random guessing corresponds to an AUC of 1/2. So if I see an AUC of just a little bit over 1/2, I'm going to be like, I don't like that model. We want AUC substantially greater than 0.5, preferably close to 1. 1 is the maximum value. We can also get the log likelihood off of our model. Usually we don't use this too much because there's no like standards. It's hard to say, is that big, is that small? AUC is good for comparing to other models. I can actually use log likelihood and AUC to compare multiple models. Log likelihood is actually part of the AUC computation. AUC takes the log likelihood and then hits it with a penalty. And so we want to have on both of these, or we want an extreme value. We want the largest value possible for log likelihood, but we want the most negative, the least value possible for AIC if I'm comparing multiple models. We can also run residual analysis and plot the residuals. Notice that we've got some weirdness going on with a few of these poisonous mushrooms. And we can use cross-validation to get a better feel for what's going on. We can do our train validation and test statistics for any statistic we're interested in. And we can use bootstrap resampling. So here, what we would do is I would sample with replacement my number of observations from my data frame, rebuild the model, and then all the data points that were not in that resampling are used to check to see, I treat them as like my test data, my holdout data. Now, so far, we've only talked about logistic regression with two levels for the target variable. Well, it's possible that we could have others more than two levels. And so 3, 4, 5, whatever. And that will be a multinomial logistic regression model. And so here, what we're going to end up doing is we're going to do log odds, but we're going to do log odds for one level at a time. And so probably the most common version of multinomial regression is in NNet. It also has a neural network function. And we can see it did a decent job on this data set. Not 100% accurate, but pretty close. So we have 3 different levels, and we're trying to model which value it is with the iris data set. All right, well, that's all I've got for you. Oh, say. For your homework assignment, first thing you're going to do is just, get your binary target variable, start modeling, evaluate your model's ROC curve and AUC. Go ahead and try multinomial logistic regression and just see how does it work out. And then analyze your odds ratio by your coefficients. Take your coefficients, analyze your odds ratio, see how much it changes, by the coefficients. And then think of a way to improve your model. All right, well, that's it for me. Life is short. Do math.